Hi all, welcome back to the discussion on quantum mechanics. So in this particular session, I'll be discussing the representation of vectors and operators in discrete basis. Okay, usually what we'll do is we'll start with a very simple example. So consider a representation of vectors in three-dimensional vector space. So consider a vector A in three-dimensional vector space. So this vector A, usually we can write as it will have some x component times I plus y component times j plus z component times k. So here I, j, k is a complete basis. Okay, so it is the collection of the linearly independent vectors in the three-dimensional vector space. So we can represent any vector as the superposition of the I, j, k vectors. Okay. Now this ax, ay, az are the components of vector A along the x direction, y direction, z direction respectively. So if you visualize it, so this is the case. So we'll have a vector x-axis, y-axis, z-axis, and I've drawn some vector. Okay, sorry. I've drawn some vector like this. So this we can, it will have some z component. So if you project it on the XY plane, we'll get a projection like this. And obviously it will have some X component and some Y component. Okay, so if this is vector A, so this length is said to be the X component of vector A. This is the Y component and it is the Z component. Okay, so this meaning is very familiar to all of you. Okay, so in those terms on this the components of the vectors, we can represent the vector A. Now the same vector we can represent in the matrix form in this way. So this vector A can also be written as Ax, Ay, Az. So remember this Ax, Ay, Az are the three components of vector along the x, y, and z direction. Okay, now we have to generalize this to n-dimensional vector space. So better we can represent this ax, ay, az in another way. This ax can also be written as the dot product between or scalar product between the unit vector I and a, and ay can be written as the scalar product between j and a, and az can be written as the unit vector, the dot product between the unit vector k and a. Okay, so this is a way of representing vector in the normal three-dimensional vector space. Okay, now we can go to an n-dimensional vector space. Okay, so consider n-dimensional vector space in which the ket phi n is, okay, let us suppose it is an orthonormal basis like your ijk. So what is going to be orthonormal basis? The inner product phi I, phi j would be delta ij. Okay, then the scalar product with the same vector will give 1. The scalar product with a different vector will give 0. So that means the different vectors will be orthogonal. Okay, so then since this the ket phi n, the set phi n are the orthonormal basis, then we can expand any vector psi in that vector space can be expressed in terms of psi n. So in terms of phi n. So how we can write that? The vector psi can be written as sum over n from 1 to capital N, where capital N is a dimension of that vector space. Then the expansion coefficient Cn times phi n. Okay. So this Cn is the coefficient of the vector psi along the direction of the ket phi n. Okay, so the Cn will have the term C1, C2, C3, etc. Cn. So we'll have n coefficient because the reason is we have total of n basis vectors. So phi 1, phi 2, etc. up to phi n. So we have n basis vector. So corresponding to along the each basis vector direction, we'll get the coefficient. Like here we have ijk. Along I, the component of the vector is ax. Along j, it is ay. Along k, it is az. So similarly, along phi on the coefficient is c1. Along phi 2, the coefficient is c2, etc. And along phi n, the coefficient is cn. Okay. Then if you generalize this way of representing to n-dimensional vector space, how will we write the vector psi as the matrix? So the vector psi can be written as C1, C2, C3, etc. up to Cn. So this is a very simple way of representing vector psi. Now so the C1, C2 up to Cn are the expansion coefficients of vector psi along the different the basis vector direction. Okay, now there is a very compact way of representing it in another way. So okay, we can express C1 as the inner product of the phi 1 psi. So like here, the ax we have written as I dot a. So similarly, C1 we can write as phi 1 inner product phi 1 psi. Okay, so better we can prove that. Okay, so this is your the ket psi. So take the inner product of ket psi with phi I in general. Okay, where I is some arbitrary number. So consider the inner product phi I psi. So that would be equal to sum over n equal to 1 to capital N Cn inner product phi I phi n. And according to the orthonormality condition, the inner product phi I phi n can be written as delta In. So sum over n equal to 1 to n Cn. This would be the canonical delta In. So this canonical delta In would be 0 when I not equal to n, and it will be 1 only if I equal to n. So here n is running from 1 to n. So among this summation, at some time n can become I. When n become I, this would be 1. All other times it is 0. So therefore, this summation would give the result Ci. Okay, so this expansion coefficient Ci can be written as the inner product phi I psi. So if you use this result, we can write your vector psi as the inner product phi 1 psi, the inner product phi 2 psi, etc. up to the inner product phi n psi. So this is the matrix representation of ket vector psi for the vector in n-dimensional vector space. Okay, so if it is an infinite dimensional vector space, the only thing is this would be an infinitely long column vector. That is the only difference. This will become phi 1 psi, phi 2 psi up to, it will go up to infinity, because there will be, in case of infinite dimension vector space, obviously there will be infinite basis vectors. So it will have infinite components. So that is the only difference. Okay, so this is for the representation of a ket vector in matrix form for n-dimensional vector space. Okay, so better we can write the matrix representation of a vector in n-dimensional vector space. This can be written as a column vector, and so this will have total of n rows and 1 column. So obviously, when for infinite dimension vector space, only difference is this, simply this n will tends to infinity. That is the only difference. Okay, all other things will remain same. Okay, now we have to recall one condition. So in order to expand the vector psi in terms of phi n, this phi n must be a complete basis. Okay, so remember this get phi n must be a complete basis. So it should satisfy the completeness condition. What is the completeness condition? I think that we have proved it earlier. That is sum over n, the outer product phi n must be equal to identity. So this is what is meant by the completeness of basis. Did we prove it or not? That we are not sure. Okay, if it is not proved, we can prove it now itself. Okay, so we have already said that this vector psi can be expanded as n equal to 1 to capital N Cn phi n. Now, according to our expression for the expansion coefficient, the Cn can be written as the inner product phi n psi phi n. Okay, now this phi n psi is just a number, so it doesn't matter whether you write this phi n psi on the left side of get vector or right side of get vector, because it is not an operator, it is just a number. In general, it is simply a complex number. So therefore, we can write this as sum over n equal to 1 to capital N phi n psi. Now, what is the left side, which is get psi? Now, if you look at this, we can see this summation as sum over n equal to 1 to capital N, the get phi n bra phi n times psi. So the psi is there on the left side itself. So therefore, this summation must be equal to identity. Okay, so if a vector can be expanded in terms of the basis vector, so that basis vector must satisfy this condition, the sum over n, the get phi n, the bra phi n must be equal to I, n equal to 1 to n. Now, what is this actually? So this outer product, we can call it as the projection operator. Okay, so this outer product is nothing but the projection operator of the nth basis. Okay, so therefore the sum over n equal to 1 to n, the sum of all projection operator would be identity. So this is nothing but the completeness of basis. The sum of all projection operator must be equal to the identity. Okay, so what we have done is we have expressed our vector psi as phi 1 psi, interpret phi 1 psi, phi 2 psi, etc. up to phi n psi for a vector in n-dimensional vector space. So there will be n rows and one column. Now, similarly, how can represent the bra psi? So since it is a kid psi, the bra psi, it is the Hermitian conjugate of this. So this would become a row matrix. The first element would be phi 1 psi complex conjugate, phi 2 psi complex conjugate, etc. Phi n psi, the complex conjugate, and there is one row and n column. So that will be a row matrix. So this the symbol representation of the vector of an n-dimensional vector space in the matrix representation. Okay, and this matrix representation will be used for in case of discrete basis. Okay, so remember here the basis vector is a discrete basis, because here n run from 1, 2, 3, etc. It is not a continuous basis. So the basis is discrete. So in such case, we can easily represent the vector in the matrix form. Okay. So next we can discuss about the operators. Okay, so this is the representation of vectors. The represented vector in discrete base. Next, we can discuss the representation of operators in discrete basis. Now the operator A It is some mathematical quantity which transform one vector into another vector. Now, how can we represent this vector in terms of a discrete basis? So again, consider a discrete basis. The ket phi n, which is complete. If it is complete, then we can write sum over n from 1 to n. The outer product phi n would be identity. Okay, so therefore your the operator a we can write as I times the operator a times I. Now what is I? So I we can write as sum over n equal to 1 to capital N phi n operator a sum over m equal to 1 to capital N phi m. So this can be written as sum over n equal to 1 to capital N sum over m equal to 1 to capital N the ket phi n, the bra phi n, operator a, ket phi m, and bra phi m. Now this inner product is just a number, so we can write in at any position. So this can be written as sum over n equal to 1 to n, m equal to 1 to n, phi n a phi m, the outer product phi n phi m. Okay. Now this quantity, this inner product, we can call it as a n m. So therefore, this can be written as sum over n equal to 1 to capital N, sum over m equal to 1 to capital N, a n m, the outer product phi n phi m. So this is your operator A. Now you will wonder how we can represent this as a matrix. So in order to know how to represent it as a matrix, so we should recall our vector representation. So recall any vector psi, the ket vector psi can be written as the inner product phi 1 psi, inner product phi 2 psi, etc. up to the inner product phi n psi for a vector in n-dimensional vector space. Okay, then how will you represent the ket phi 1? So ket phi 1 can be written as the inner product phi 1 phi 1, the inner product phi 2 phi 1. It is in terms of instead of psi we have to just substitute phi 1, then inner product phi 3 phi 1 and up to the inner product phi n phi 1. Now this ket phi 1 is an orthonormal basis, so therefore the first inner product would become 1 and all other inner product would be 0. So it will be an n by 1, the column matrix. So that is the representation of ket phi 1. Then what would be ket phi 2? So ket phi 2, that would be phi 1 phi 2, that would be 0, phi 2 phi 2, that would be 1, then 0 0 up to 0. Then ket phi 3, that would be 0 0 1 0 0 etc. up to 0. And finally what would be ket phi n? That would be 0 0 etc. The last quantity would be 1, n by 1 column matrix. Okay, so that's it. That is a representation of each basis vectors. Then how would be the outer products? So what would be the outer product? Phi 1 phi 1. So this, the first would be the ket phi 1 would be a column matrix 1 0 0 etc up to 0. The bra phi 1 would be a row matrix 1 0 0 up to 0. Now this outer product will give 1 0 0 0 0 0 0 0 0. All others are 0. Okay, only the 1 1 element would be 1. And similarly, what would be the outer product phi 1 phi 2? The outer product phi 1 phi 2, that would be 1 0 0 etc up to 0. This would be 0 1 0 0 etc up to 0. So this is 0 0 0 etc up to 0. Sorry, here you will get a 1 here, and all other will remain 0. So that would be phi 1 phi 2. Now what would be the outer product phi 2 phi 1? Outer product phi 2 phi 1 would be 0 0 up to 0. So this would become 1, and all other would remain 0. So in general, this phi outer product phi n phi m will have 1 only at n mth element. It's nth row, mth column. So remember this phi 1 phi 1, the outer product phi 1 phi 1 will have the element at first row, first column. Phi 1 phi 2, the first row, second column. First row, second column. And phi 2 phi 1 has the second row, first column. Then phi n phi m will have 1 only at nth row, mth column. So if that is okay for you, then we can expand this matrix representation. So your matrix operator A is sum over n equal to 1 to capital N, m equal to 1 to capital N, A n m, the outer product phi n phi m. So that means you will have summation A11 outer product phi 1 phi 1 plus A12 the outer product phi 1 phi 2 plus A13 the outer product phi 1 phi 3 etc. A1n the outer product phi 1 phi n plus A21 the outer product phi 2 phi 1 A22 the outer product phi 2 phi 2 etc. A2n the outer product phi 2 phi n. Then finally the last line, that would be an1 the outer product phi n phi 1 an2 the outer product phi n phi 2, and last element would be ann the outer product phi n phi n. So if you sum all these elements, what will you get? We'll get a very big matrix. Okay, so this the first matrix would be an n by n matrix. It will have only one element A11 that will be in the first row, first column. And second element, second matrix is again a big matrix, n by n matrix, and it will have only one element A12 in the first row, second column. Next would be A13 up to we'll get A1n. Then you will have A21, A22, A23 up to you have A2n. Then AN1, AN2, AN3, etc. up to ANN. So this would be the matrix representation of operator A. So we can represent the matrix representation in the inner product way also. So it's A11 is nothing but phi 1 A phi 1. A12 is phi 1 A phi 2. Then phi 1 A phi 3, etc. up to phi 1 A phi n, phi 2 A phi 1, phi 2 A phi 2, phi 2 A phi 3, etc. up to phi 2 A phi n. Now the last line would be phi n A phi 1, phi n A phi 2, phi n A phi 3, etc. Phi n A phi n, and that would be n by n matrix. So in n dimensional vector space, the operator is represented by the n by n matrix in discrete basis, and the bases are represented as phi 1, phi 2, phi 3, etc. And the elements would be the inner product. So you have to sandwich the operator between phi 1 and phi 1, that will give the first row, first column element, and the first row, second column element would be the inner product phi 1 A phi 2, etc. And you can get the complete representation or complete matrix element of the operator, and we can represent an operator in the matrix form. So this is a discrete, is a representation discrete basis, and for a finite dimension, and for infinite dimension, again in discrete basis. So all above discussion is true. Only thing is you have to just replace, or you have to just represent that n, capital N tends to infinity. The dimension of the basis will tends to infinity. That is the only difference. If it is a discrete, when it become continuous, then the issue is different. We cannot represent in this particular form. Okay, this simple way of representation cannot be possible. So that we will discuss in the next session, is how to represent the vectors and operators in a continuous basis. Okay, so here we are represented as a discrete basis, and for discrete basis, the matrix representation gives a very elegant way of representing the vectors and operators. Okay, so that's all for now, and we can stop it here. Okay, so in this entire discussion, we have assumed our basis is complete. Okay, there is sum of all projection operator of the basis gives identity. Okay, so thanks for watching this video, and we'll come up with representation continuous basis in the next class. See you then. Bye.